Hello everyone. You have already familiarized with the concept of text classification in NLP. Today I'm going to give you a tutorial on the text classification task. So we can approach the problem in different way. So in this tutorial, I am going to give you two different approaches, one using static embedding and another using BERT embedding. Particularly in text classification, we are focusing today on the sentiment analysis task. So in sentiment analysis, whenever we are given a review or a comment, we have to find out the emotion attached to the particular text. So before going to the process of text classification, let's first start familiarizing the glove word embedding. So first we start with downloading the embedding from its official website. So when you download it, you will get the embedding in different dimensions. For this task, today I'm using a word embedding of 100 dimension. So we open that particular file, and in that file you'll have words and corresponding word embedding. So I'm taking those values to a dictionary structure, and I'm naming it as embedding index 100 dimension. So after reading the whole file, we'll be having these many words and corresponding word embedding in that. So for example, I can show you how an embedding of a particular word look in this glove embedding. So we are taking a word movie, and that particular embedding has a size of 100 because we chose 100 dimension. And this is how the embedding of that particular word look like in the glove embedding. Now we can have for the how to understand how words are represented in that embedding space. We are going to find out word embedding for certain set of words, and we are going to plot it in 2 dimensions. So these are some example words. So using this distributed stochastic neighbor embedding, we are plotting these words. So you can see the words are having positive and negative emotion associated with this. So accordingly, these words have been plotted in 2 dimensions. When you have a word embedding, we can find out cosine similarity, which is a commonly used similarity score between words or context. So we are going to find out this cosine similarity between any given word. So this is cosine similarity. So here is an example. We are taking the word film and movie and find out their cosine similarity using glove 100 dimension embedding. So we are getting the cosine similarity of 0.9. And we can use different embedding. So if I'm trying with another embedding of 300 dimension, we have to still load all the words and the corresponding embedding from the file that we have downloaded. Then using that dictionary that we generated, we can find out the embedding for all the words and cosine similarity. So if you check the cosine similarity, the value is changing differently because when we increase the dimension, we are exploring more fine-grained information, semantic information. So that is why the cosine similarity changes when we change the dimension of embedding. Now coming into text classification. So as I said earlier, we are going to find out the sentiment associated with particular review. So we are having a data set taken from IMDb. So we want to do some pre-processing before doing the embedding. So in the pre-processing, we will first convert into lowercase letter, lowercase words, because in the glove embedding, we are having all the lowercase words and the corresponding vectors. And then we have to remove the punctuations. We tokenize this text. Tokenize means when we are given a sentence, we convert into words. Then we can also remove the stop words, which are very common in both positive and negative reviews. So which will not be contributing towards understanding the meaning of that particular sentence. So to do this, we take all the necessary libraries from NTK, stop words, word tokenize, and all the listed libraries. So in the data set that we have loaded from IMDb, this is the data set which has 50,000 rows and 2 columns, reviews and sentiments. For a classification purpose, we have to change this sentiment into corresponding labels. So this positive sentiment we are converting into, we are giving a label 1, and negative sentiment we are giving a label 0. So now from now onwards, we will be dealing with only the review and the corresponding label. So to do the classification purpose and to train the model, we first do the data splitting. For splitting the data into train and test model, we use the train test split from sklearn library. So once the data is split into test and train, we can do the pre-processing on them. Then now we will be having a set of words in each of the reviews. Now we find out unique words which are there in each review. And for each of the words, we will find the embedding. So whenever we are given a review, we pass that whole pre-processed review to this paragraph embedding function. And in this function, you take all the unique words, and for each words, you find the vector embedding, glove embedding from the dictionary that we define. So then, so it will have different vectors for each of the unique words available in that review. And now we do the mean to get the word embedding for that particular sentence. So in the train and test data, we do the same processing, because if you're training a model on which has undergone certain pre-processing, we have to do the testing on the similar data which has undergone the similar pre-processing. So once all the pre-processing and embedding is done, this is how your one data sample looks like, which will be again a 100-dimension vector. Now we take a logistic regression from the sklearn library, and we fit the training data on that particular model. So we use accuracy score, precision score, and all the evaluation metrics, and we test this fitted model on the test data, and we get the accuracy of about 79%. So this is calculation is done on whole test data. So if we can check it on any other random text. So this is an example text in which I have to do the pre-processing, do the paragraph embedding. Then if I can predict, it is predicting it as a positive class. So that is how we do text classification using glove embedding. Now that we have explored text classification using glove embedding, let's see how we can do this task using BERT. So BERT is a transformer-based model, and its specialty is that it can understand the contextual meaning of words in a sentence. So in glove, for one particular word, we had a fixed embedding, but in BERT, it is not the same. So based on the context in which we are using, the word embedding changes. This is a BERT-based model, which is pre-trained on large corpus of data, and we can fine-tune it for any downstream NFP task using appropriate data sets. So here we are going to use it for text classification. So the first library that we wanted, which is the most important library, are transformers. So we are using multiple functions provided by this library. Then we need OS and torch libraries, because they are also providing a lot of functions which we will be using during the tutorial. Now we start with loading the data set and pre-processing it. We are using the same IMDb data set, and to load them, we use the pandas library. So we have the review and corresponding sentiment, and we have to again convert the sentiment into classification labels and we map the positive to 1 and negative to 0 like we did earlier. And in this particular process, we are not keeping them as data frame as such. We are converting the text and the labels into lists. So we have the whole data set converted into text and labels. We have to split it into test, train, and validation data. So we are taking a ratio of 20% for test data, and the remaining will be trained. And out of the 80% remaining, we will again train into a validation data set. So we are using the train test split model from the sklearn library, and we are specifying the ratio in which the splitting has to be done. So first we split the actual text and label to train and test. Then the train, we again split into train and validation. So now we have the data as text and labels, but as we are giving this to as input to our transformer model, we have to make necessary changes. But we don't have to define any pre-processing as such. We define for the glove-based glove method, but here the transformer itself provide tokenizer which will pre-process which will take the whole sentence as such and do the pre-processing accordingly. So to do that, we take BERT tokenizer from the transformer library, we take the dataset library from Torch. And in this tutorial, we are using BERT model, BERT based uncased model. And we are defining the max length to be 128. So to do this pre-processing, we are defining a text classification dataset class, which takes the text, labels, tokenizer, and maximum sequence length of the transformer, and it calls the tokenizer function. The tokenizer takes the text and the max length it returns a tensor, and it does padding and truncation. Padding means if we have fixed the maximum length of the input sequence we are processing, which is 128. So if the input we are giving is not 128, it's less than that, then we add padding so that all the input are of equal length. And if the input text has a size greater than 128, we truncate it. So after doing all this, it will give you a output. We call it encoding in this case, and we are passing the encoding will have 3 components: input ID, attention mask, and token type. We have to pass the input ID and attention mask to the transform model as inputs and label as the output. So we flatten input ID, attention mask, and we already have the labels. So we convert them also into a torch tensor so that it can be processed by the BERT transformer model. So let's see what actually happens inside the tokenizer and what are the output you are getting from the tokenizer. So I'm again defining the tokenizer, and this is a sample text. This movie is one of the best production I've seen in years, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 words in it. So we call tokenizer with that text, and it returns you a dictionary. And the dictionary are, as I said earlier, input ID, token type ID, and attention mask. It has a size of 128 because we fixed the maximum sequence length to be 128. Now we'll explore what are content in each of the section. So input ID has the input ID taken from the BERT vocabulary. That is, if you have a text, if you have a word, it search in the BERT vocabulary and take the corresponding ID for that text. So these are the IDs corresponding to our input text from BERT library. But you can see the IDs, how many IDs we have: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We had only 13 words in the text, but here we have 16 tokens. Why there is a change? I'll come to that in a bit. And here in the beginning of the processing, we don't know what are the token types, so we are all keeping them to be 0. We are not differentiating them. And attention mask means to which of the words or which of the IDs you have to give attention to. So we are keeping all the attention 1 to all the non-zero IDs, and the 0 IDs are the padded IDs, so that the input become of length 128. So now let's see what are the extra token IDs that is added by the tokenizer. So we are using a convert ID to tokens method provided by the tokenizer to get the details. So you can see a sequence start with a special token called CLS. So there's a CLS token followed by each of the words in the input that we have given. And there is full stop, which is also considered as one token. And we are using separator to separate between different sequences. Then it is followed by the padding. So that is why there is a difference in number of words in the input and the tokenized IDs we are getting from the tokenizer. So with using this class that we defined earlier, we are generating train data set and validation data set. So we pass the train label, train text, tokenizer, and maximum length to the classifier, and we get the training data set. And we pass the validation text and label, you get the validation data set. Now, when we are passing input to the BERT model, we are passing it in a batches. So, and how we handle the batches, that is done by data loader. The data loader function is provided by Torch, and we are, in this particular case, we are fixing the batch size to be 16. So we give the training data set and the batch size, and we are asking it to shuffle the training data set, and using the data loader, we are defining the train data loader variable. And similarly, we are also using data loader for getting the validation data as well. So now we have the data. Now we have to make the changes in the BERT base model so that it can be acted as a classifier. So this is what we are going to do. We take this is the base BERT architecture. We give the input sentence tokens, and from the CLS token, we take the attention weights and pass it to a fully connected layer, which act as a classifier, which act the purpose of classifier layer in this case. And we append it with the activation function, softmax or tanh, anything which is available according to our requirement. So let's see how we can implement it using from our base model. So we are again defining a new class, which is BERT classifier, in which we take the BERT base model and append the classifier features to that particular model. For that, we require a neural network library from Torch, and the BERT, we are taking the BERT model from transformers. So when we are initializing, we take the base model from pre-trained. Then we add a dropout layer on top of that so that it doesn't overfit. And then we are adding a classifier layer, which is a fully connected layer, which has a dimension from hidden size of the model to the number of classes. So it will here in our case, this number of classes is 2. So based on our classification task and the data set we are using, we can change the number of classes. Now we have to make the changes in the forward pass of the transformer so that this classification is happening. So we have the input, we are passing input ID and attention mask as input. We process this input using the basic bird model first. We get the output. So this output has many components. This last hidden state is one of the component which give the attention mask of the last hidden state of the model. Here we are not using that feature anyway, but I've kept it for the purpose of understanding and explaining. And but the one component that we are interested in is the Pooler output, which is the pooled representation from the CLS token. And that output we are passing it to the dropout layer that we added, and then we apply fully connected layer on that result and do the sigmoid activation function to get the logits of the classification. So the forward pass returns the logits and the hidden state in this class. So now we have the architecture altered and the data. So now we'll see how we can train the model using the data set on this particular model. So we define a training function, train, and we set which take the arguments model, data loader, optimizer, scheduler, and the device on which it is being trained. So initially we set the model in the training mode. And as I said earlier, in the transformers, we are giving the data as batches. So for each batch from the data loader, we are going to do the training operation. So we initially set the gradients in the optimizer to be 0. And we take the input ID, attention mask, and labels, and we convert into the format which is supported by the device. And we pass this input components, input ID and attention mask, through the model. You get the output. And the output is, we have the output and the actual labels that we have from the data set. We do cross entropy loss in both in them and calculate the loss. This loss is backpropagated through the network and the weights are updated accordingly. And the optimizer and scheduler helps to do the process. Once we have the train function, we'll define an evaluation function. So in the evaluation function, we are using two matrices for evaluating the model, accuracy score and classification report, which are from the sklearn library. So in the beginning of the procedure, we set the model to evaluation mode, and we initialize to list prediction and actual labels. And here the evaluation we are doing on validation dataset. The training we did on training dataset. So in each batch, we load the validation dataset. We take the input ID, attention mask, and label as we did in the training, and we pass the input components through the model. We get the output, and we do the argmax to get the class label for that corresponding output. So now you have the predictions and the actual labels we already have. So we convert into a format that can be processed by the accuracy score function and classification report function, which are lists. Then we do the evaluation using these predefined functions, and we get the accuracy score and classification report. So now we have all these components. Let's see how we can train the model. So we define the number of classes to be 2, and if GPU is available, we will use GPU. Otherwise, we will use CPU as our device, and we initialize an instance of the new bird classifier class using the base model and the number of classes. And this is how the model looks like. So all the initial components are those from the base bird uncased model, along with the components that we have added for classification purpose. So you can see there is embedding, word embedding, position embedding, token type embedding. The word embedding has a size is 30,522 to 768. So this 30,522 is the vocabulary size of bird, and 768 is the hidden state size. And we have the position embedding, token embedding, and one of the main component of BERT is its encoder stack. So we have 12 encoder modules, and each encoder module have these many components, which are the main component is attention module. Attention we are doing using query, key, and value calculation, which we usually do for transformer models. Then there will be linear layer on top of that, layer normalization, dropout as output to the attention. Then in the intermediate, we'll have a linear layer on top of that. Then again linear layer and layer normalization. And after all the stack of encoder, we will again have a polar layer, which is a linear layer. And on top of that, we have added a new dropout layer and a fully connected layer. So in the fully connected linear layer, you can see the input is 768, the hidden representation size, and the output size is 2, which is the number of classes for our classification task, which we defined, which we passed when we created that bird classifier class. So now we define number of epochs for which the model need to be trained, the learning rate, and we have to initialize the optimizer and scheduler. So these initialization are done with the help of transformer library. So these are actually hyperparameters which you can tune, which you can change according to your requirement and find out which one best suits your task. Here I'm not going to use it. I've just fixed the hyperparameter for now. And now we train the model. Actually, I did the training on GPU module because it takes a lot of time. It's a transformer model. So I'm just showing only the results after the training. So in the training, you take for 5 epochs, you are calling the train method and doing the calling the evaluate method. You get the validation accuracy and accuracy report for each of the epoch on the validation dataset. So this is the report over epochs. So you can see from the first epoch, it's 0.87. And when it reaches the 5th epoch, it's 0.88, which means the training has an effect on the model and the model is training better over iterations. So once we train the model, we can always save it so that we can use it anywhere. And the torch helps us to do that. Torch provide a torch.save method using which you can save the model that we trained. And it again provide a load model.load state dictionary method in which you can load the saved model. So actually, whichever device you are using, whether GPU or CPU, the code is a little different. And once we load the model, so now we use the train dataset for training and validation dataset to check the improvement of the model over iteration. So now we have the final model. Let's see how the model perform on a test dataset. So you have to generate the test dataset using the test classification dataset like we did for train and validation. Then you have to do the data loader so that it takes the data in batches to the model, and we use the evaluate method to find the accuracy and the performance results. So the test accuracy says 0.8899, which is around 90% test accuracy. So this is a result over a test data set. So let's see how we can do it on any individual review. So if you are given with a review, how you can find the sentiments of that review. So for that, I'm defining a prediction function. So that takes the text, model, tokenizer, device, and max length as parameters. So we do the we apply the tokenizer on the text so that we get the input ID and attention mask. The same way we pass it through the model, we get the output. We do the argmax to get the predicted labels. So if because we have mapped the sentiment positive, negative, the 1 and 0 labels, we have to map it back. So if the predicted label is 1, we say the sentiment is positive, otherwise it is negative. So, and we can print the text and corresponding sentiments. So here are some examples I took from the text sets, test text, some random examples. So here you can see one example, finally, an Indian film that actually delivers some great scares. So which is a positive sentiment in terms of the movie. So it's predicting it's that positive. And here is another random text. I'm sure this is a masterpiece from the director. It is again saying it's a positive review. So yes, that is all from the tutorial. Thank you.